Hello, algebra students. Today we are looking at patterns and nth terms again, and we're going to learn a new type today. This will be the last type we learn. It's a very important type. But first, I want to quickly review that. Remember, we know about linear patterns, right? And the way we identify if a pattern is linear, remember the exponent would be something like this. It might be like, say, n plus 5, right? That would be linear. And that happens when the first difference is always constant, right? Okay, we also know about achoo. Oh my goodness. Quadratic patterns. And quadratic patterns would look something like this. Say an n squared minus 2, right? Or even an n squared plus n plus 1. That would be quadratic as well, the highest power being 2. And quadratic patterns show up when the second difference is always constant. We've also learned about cubic patterns. And cubic patterns could be something like this. N cubed minus 2n plus 1, where the n cubed, the third, 3 is the highest power. All right, and those show up when the third difference is the same. And then there's quartic, which is when your exponent is to the fourth power, n to the fourth plus n. That could be quartic, okay? And that's when the fourth difference is the same. But we are going to look at a different type of pattern, a pattern called exponential. Yeah, nice big word, exponential patterns. All right, and we'll find the nth term with them. Let's take this set of numbers here, and I gave you more numbers than I normally get. What I would like you to do is to pause the video and go ahead and make your table and find the first, second, and third differences. Okay, and when you're ready, unpause the video and see what happened. Okay, see if you got the same thing I got. All right, if you're still watching at this point, I'm assuming you're wanting to see what's going to happen. So you see, here's my table, and remember I'm in search of the nth term. And so when I go looking for my first differences, I got what? Plus 2, plus 4, plus 8, plus 16, plus 32, plus 64, plus 128. I don't know if it strikes you as odd, but notice these numbers line up. You see that? Like you're adding the number to itself. You know, 2 and 2 is 4, 4 and 4 is 8, 8 and 8 is 16. Okay, well, then when you go for the next difference, watch what happens. You get plus 2, plus 4, plus 8, plus 16, plus 32, plus 64. Now, some of you say, well, the 128 dropped off. No, actually it didn't. If I did the ninth term and the first difference, the second difference, I get a plus 128. Okay, so it's not actually getting smaller, it's just that I'm running out of data. And then if I go third differences, I get plus 2, plus 4, plus 8, plus 16, plus 32. And again, if I do the ninth term and the 10th term and I did the first and second differences, I would get 64 or plus 128. The point is, this is going to go on forever. Okay, this is going to go on forever. This is not going to work. It's not a linear pattern. It's not quadratic, not cubic, not quartic. This method is not going to work for this pattern. But there's two ways I want to explain this to you. One thing you might notice, you might notice that the numbers are doubling. So you do times 2 and times 2 and times 2 and another times 2. And that is like a constant quotient, right? The quotient is, or the product is to double. If that happens, then this fits some pattern like 2 to the power n. Okay, and I'm going to prove that to you another way. I just told you that if this happens, if it doubles every single time, it's going to be like 2 to the power n. If it triples every single time, it'll be 3 to the power n. But let me kind of give you a better visual on that. Do you know a different way to write 4? I could write 4 as 2 to the second power, right? 2 to the second power would be 2 times 2, and that's 4. I could write 8 as 2 times 2 times 2. But the shorthand way of saying that is 2 to the third power. I could write 16 as 2 times 2 times 2 times 2, doing the prime factorization, of course. That would be 2 to the fourth. Of course, that makes 2 to the first. 32 would be 2 to the fifth. 64 would be 2 to the sixth. 28 to the seventh. 256 to the eighth. Well, when I get to the nth term, what will my formula be? It'll be 2 to the power n. And then once I know that, then I could find whatever number I wanted. Word of caution here, if you try like 2 to the 100th power, okay, on a calculator, that is going to be a very, very large number. In fact, in some situations, I think 2 to the 100th will work, but in some situations, you'll get a number so big, you'll go into scientific notation, and also possibly your calculator will not be able to handle the number. You'll get an error. Yeah, 2 to the 100th, I end up getting this number here. Hold on a second. I get 1.2676506 times 10 to the 30th power. Remember scientific notation. If I want to convert that to a regular number, a standard number, I have to take that decimal point and I have to move it 30 places to the right. In fact, I have to multiply by 10, 30 different times. That's what I'm doing. I'm multiplying by 10. Each scoopy is to multiply by 10. So let me rewrite the number without the times 10 to the 30th. 1.2676506. And I don't know if I'm going to have enough room, but I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I have to put zeros in all of those little scoopies. And I don't think I want to draw them all. So I'm going to try this. Okay, instead of making you watch me fill in all those zeros, I just paused the video and showed you the black zeros are the new ones. And they probably wouldn't all be zeros, but the calculator couldn't show all the numbers. And there you go. So that number is at least that big. And look at this. This is humongous. If you stop and consider, okay, well, let's see. Right here is the millions, billions, quadrillions, quintillions, sextillions, heptillions, octillions, nonillions, decillions. This is more than 1 decillion. All right. So 2 to the 100th power is a humongously large number. All right. Let's take a look at 2 more examples here. All right, here's a pattern, and I'm going to fill in first term, second term, third term, fourth term, fifth term. I'm looking for the nth term. I'm not going to worry about like the 30th and all that. I think you guys get that part. It's pretty simple. I got to go 3, 9, 27, 81, and 243. Now, if you're pretty sharp with numbers, you might notice that it's times 3 every time. Right? 27 times 3, 81, 81 times 3, 243. You might want to verify that. Or you could think of this as 3 to the first, 9 is 3 to the second, 27 is 3 to the third, 81 is 3 to the fourth, and then 3 to the 5th. Therefore, the nth term must be 3 to the power n. And that's your formula. That is your term. These are exponential. Now, sometimes they're going to look really strange and they're not going to be so obvious. Move that up a little bit there. Oop, I don't think I can move that one up. Okay. But let me fill it in. 1, 2, 3, 4, 5. And then, of course, I'm looking for the nth term. I've got 1, I've got 7, I've got 9. No, I don't. I have 25. Where I got 9 from, excuse me. 25, 79, 241. And, if I do the first differences, I'm not going to have any luck. If I do the second differences, no luck again. Third differences, If I try to double or triple them, that's not going to work either. But if I check out this pattern here, and change the color of it, I'll make it pink. Red's orange. There we go. I'll make it orange. Shows up pretty good. If you look in the table here and compare these orange ones to the black ones in the table. So, 3 turns into 1. Well, it's minus 2. 9 into 7, minus 2. 27 to 25, minus 2 again. They're all take away 2. Well, the orange pattern was 3 to the power n. So this black pattern here would be 3 to the power n, but then you'll take away 2. And then, of course, if I wanted to find the 10th term, I would do 3 to the 10th power, take away 2, which is quite a large number. Hold on one second here. Let's see, 3 to the power 10 minus 2 ends up being 59,047. That's a very large number for only being the 10th term of the sequence. Okay, if I did the 100th, I'm going to get a humongously large number in scientific notation. 3 to the 100th power minus 2. It ends up being about 5.15 times 10 to the 47th power. So the last one had 30s, scoopies, if you call them that. This one would have 47, multiplied by 10, 47 different times. Okay, so that's your lesson for today, exponential patterns. All right, Mr. Lawrence signing off.